Okay, let's try doing this a little bit differently. So, some of you might remember the 2000 Olympic Games that were held in Sydney, Australia. There was an athlete named Marion Jones who competed in track and field. She won 5 Olympic medals, 3 golds and 2 bronzes. And one of the golds that she won was in the 100 meters. And that's what we have up there, the 100 meter finals with her and her 7 competitors, so 8 total. And Marion Jones, as you can see, she ran 10.75 seconds. And if you look at her 7 competitors in the finals, nobody else even broke 11 seconds. So she was a lot faster, obviously, than the rest of the field. So what we want to do now is see if Marion Jones's time of 10.75 is so different from her competitors that it reaches a level of statistical significance. And we can do that by getting a z-score. So the first thing we do is we know we have an n size of 8, so we can add up the 8 scores and divide by 8 to get the mean. And we see there we have a mean of 11.145 seconds. Then we need to get the standard deviation, and I'm not going to go through all this, but we remember the way that we get it is we take each individual score, subtract the mean, and square it. Then we get the summation of all those and divide by n minus 1, or which ends up being 7, and that gives you your variance. Then you get the square root of your variance, and that gives you your standard deviation, which, as we can see up there, is 0.1664. So once we get that, we can get a z-score. Okay, so then if we look at the upper right-hand corner, we can see our z-score formula, which is you take any individual score minus the mean and divide by your standard deviation. Now we could do that for any one of these 8 athletes' times, but again, we want to focus on Marion Jones to see if she's an outlier that's so different that it reaches statistical significance. So here let's focus on the z-score formula again. So we can take Marion Jones's time of 10.75 minus the mean of 11.145 and then divide by our standard deviation of 0.1664. Go down one step, you get negative 0.395, again divided by your standard deviation, 0.1664. And you end up getting a z-score of negative 2.37. Now at this point, go to your Appendix B in the back of your book. If you look under column A, you'll have your z-scores. So find 2.37, and you want to look for your area beyond z now. Okay, so now let's focus on the bell curve here. So 2.37, again we have a negative one, so we're going to be looking at the left side of the curve. Under column B, you have the area beyond z. And that says 0.4911, right? If you go to 2.37, look over to the right, it should say 0.4911, and that's your area between the mean, or the middle of your bell curve, and the z-score of 2.37. In this case, we're looking at negative 2.37, or that represents 49.11% of the left side of the bell curve. Now let's look under column C where it says the area beyond z, and it should say 0.0089. That's the portion in what's called the tail. In this case, it's the left side of the tail. The further away you are from the mean, the z-score is away from the mean, the more unique or significant the score is. So if we have an area beyond z of 0.0089, that's actually less than 1%, meaning it's very, very significant. We can actually look at our thresholds for significance if we look at the z-scores specifically of 1.65 and 2.33. So 1.65 corresponds with an area beyond z of 0.05. Actually, it's a little bit less than that. And a z-score of 2.33 correlates with the area beyond z of 0.01. Now, the area beyond z for Marion Jones's z-score is 0.0089, which is less than both 0.05 and 0.01. So that is statistically significant at both 0.05 and 0.01. And it's more impressive to be statistically significant at 0.01, so let's focus on that one. What this means then in layman's terms is that there's only a 1% chance, or a 1% probability, that her difference, Marion Jones's difference between her and the rest of the field, happened by chance. Only a 1% probability it happened by chance. Conversely, there's a 99% probability that there's something significantly different between Marion Jones and the rest of the athletes in the field. Now that could be a lot of different things. It could be that Marion Jones is just that much more impressive of an athlete. She might be that much more innately gifted than her 7 other competitors. Or it could be something else. Remember, Usain Bolt, his time only reached a threshold of 0.05, not 0.01. Now Marion Jones, about a decade after these Olympic Games, she admitted that she was taking steroids, and all 5 of her medals that she won were stripped of her. So that might be the explanatory variable that made her time that much more impressive than the rest of the field. And when we got to that threshold of 0.01, we had to at least raise an eyebrow and say, wow, what made her so much different? Okay, that doesn't necessarily mean it was the steroids, but it's not that surprising when we take everything into account and we look at this from a statistical perspective.